All right, we're going to go over exam 4, do the solutions. Hopefully this will be helpful. Let's jump in. There it is. Okay, so identify the shortest bond. So we have a single covalent bond, double covalent bond, and a triple covalent bond. So this would be like C with one line, C with two lines to another C or nitrogen or whatever, or C with three lines to another atom. So the more bonds we have, the stronger the bond becomes, and the closer then those two atoms are going to get to each other. So the shortest bond should be the triple covalent bond. Place the following in order of increasing magnitude of lattice energy. So for lattice energy, we're looking for two things. I'm looking at what is the size of the ions involved and what is the magnitude of the charge of the ions involved. Charge is going to usually have a much greater effect. So with beryllium oxide, the charge on beryllium is 2 plus, the charge on oxygen or oxide is -2. For lithium and fluoride, it's -1 or +1, -1, and sodium and fluoride, it's +1, -1. So beryllium oxide, based on all that, should be the greatest. So right off the bat, we can see only A or B would be an option. And then between lithium and sodium fluoride, we're looking at the size of the atoms. Lithium is higher on the periodic table than sodium, so it should be smaller. So that means it can get closer to the fluoride. So we'll have a stronger lattice energy there, whereas sodium's a little larger, so it can't quite get as close. So sodium fluoride would be our smallest lattice energy, followed by lithium fluoride, then beryllium oxide. The blank cycle is an application of Hess's law that breaks down the formation of an ionic solid into a series of individual steps. So here we would look at if we have a metal and we need it to become a cation, going from a solid to a gas, then going from that neutral gas to a charged cation and losing an electron. For our anion, it might be taking on that additional electron to take on a negative charge, and then whatever the enthalpies are for those individual steps, be they endothermic or exothermic, we can add them together to find the overall lattice energy, and that's the Born-Haber cycle, C. Right, using bond energies, determine the enthalpies of the following. I won't use. Oh, yeah, here we go. Just loading the whiteboard. Okay. All right, for this one, we have C2H6. So I need to know, again, what is the actual structure of that. So I know specifically what bonds are we looking at, what bonds are being broken, what bonds are being formed. So for C2H6, we should have that. Then we have 7 O2s. That's an oxygen-oxygen double bond. And then that's all going to make 4 CO2s. CO2 should have 2 carbon-oxygen double bonds and 6 waters. So that would be each water has 2 oxygen-hydrogen bonds. We have 6 of those, so 12 total. All right, so let's go in and look at our bonds. So for this C2H6, I'm going to break 6 of those carbon-hydrogen bonds. We have 2 of those molecules, so I'm going to have 12 times carbon-hydrogen bond is 415. Then for that oxygen-oxygen, oh, actually, we're going to have to break, sorry, that carbon-carbon single bond as well. So there's 1 per molecule, 2 molecules, so that'd be 2 times 345. And then lastly, see, do I have? Okay. Aha. Then we go to our oxygen-oxygen double bond. Take that off. Well, so that'd be 7 times, let's see, oxygen is 498. And then from all that, why won't you write? Right there. I would subtract. Now I've got to break 2 carbon-oxygen double bonds for every molecule. There's 4 molecules, so that'd be 8 times the carbon-oxygen double bond is 741 plus here I'm going to break 2 oxygen-hydrogen bonds per molecule, 6 molecules for a total of 12, and the oxygen-hydrogen bond is 464. There. Okay, so I've got and we get negative 2,340 kilojoules. So there's our answer for number 4 on version A. Back to the exam. All right. What molecular geometry would you predict for PCl5? So actually, should have stayed on the whiteboard. Okay. So PCl5. Okay. So phosphorus has 5 electrons, valence electrons. Chlorine has 7. 7 times 5 is 35. So I should have a total of 40 valence electrons when this is all done. Since there's only 1 phosphorus and 5 chlorines, I'm probably going to put phosphorus as my central atom. And I'm going to do the chlorines all around that. The chlorines have 7 valence electrons. 1 is unpaired. So I'm going to use that probably to form a single bond between the phosphorus and all the chlorines. Phosphorus has or it's on the 3rd row of the periodic table, so we can use it to form an expanded octet if need be. So there's our wedge coming out of the page. Here's our dash line going out the back of the page. So I think if we do this, then I've got 6 lone pairs around each chlorine. There's 5 of those. So that's 30 electrons right there. And then I've got 5 bonds with 2 electrons in each bond. So that would give me 40 total electrons. So that matches our valence electrons. There's no overall charge. So if we have 5 electron groups and 5 of them are bonding and 0 of them are non-bonding, then the shape or the geometry we should have here should be trigonal bipyramidal, or try to sort of write it that way. I'm going to have 1 chlorine at the top, 1 at the bottom, and the other 3 are going to be arranged in that horizontal plane. Which of the following molecules would you predict to have a dipole? So C, H, 2, F2 should have tetrahedral geometry. The fluorines are much more electronegative, so they're going to pull electron density to one side of the molecule. So yes, this would have a dipole moment. Carbon tetrachloride would also be tetrahedral, but the chlorines are, well, they're all very electronegative, but that's the only satellite atom that we have there attached to the carbon. So they're all going to cancel out each other. So this would not have an overall dipole. Boron trifluoride. This is one of our exceptions where we can have, we don't have to have an octet around boron. 6 electrons will satisfy boron. So this is trigonal planar. So all the fluorines are in the same plane. They're at 120-degree angles. So they're all essentially pulling against each other, again, canceling each other out. So that wouldn't have a dipole. And then lastly is CO2, which is linear. The oxygens are more electronegative than the carbon, but they're going to pull electron density out to either end, again, essentially canceling each other out. So no, that would not have a dipole. All right, question 7. Consider the molecule below. So I've got carbon to carbon, double bond to O to carbon, and then we've got 2 hydrogens, another carbon, or sorry, not a carbon, a nitrogen. And then that nitrogen has a lone pair. And then 2 hydrogens on it. So we want to know what's the geometry of 1 and 2 and 3. Well, 1, the carbon has 3, or essentially, well, you could say 4 electron groups. All 4 are bonding, or 2 of them, though, are both going to oxygen. So we would have this as a trigonal planar. All of those bonds between the 2 carbons and the oxygen are all going to be in the same plane. For the 4th carbon, we have 4 bonds there, 4 electron groups, 4 bonding, all to different atoms. So that should be tetrahedral. And then lastly, for the nitrogen, we have 4 electron groups, 3 bonding, 1 non-bonding. So that's going to take the bonds to the carbon and the 2 hydrogens. That lone pair is going to push them down and give us a trigonal pyramidal shape. So for version A, that would have been answer A. How many sigma bonds and pi bonds would we have in C2H4? That's going to look like this. So sigma bonds or single bonds essentially here, 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 and here. So I should have 5 sigma bonds, and then, come on, I've got my pi bond there, 1 pi bond, which is the double bond from the carbon to the other carbon. What's the hybridization of the central atom in SF6? So SF6, sulfur's got to be able to form 6 bonds here. So that means I've got to take that s orbital, 2 of my p orbitals, and 2 of my d orbitals to form 6 bonds or hybridized bonds of identical energy. So that would be 1s, 3p, and 2 of the d. sp3d2 would be the hybridization scheme for SF6. Place the following elements in order of increasing electronegativity. Well, fluorine is the most electronegative, and then the further away we get from it, the less electronegative we are. So these are all actually in the periodic table in the same column. They're all halogens, and very simply, iodine's the furthest away from fluorine, so it will be the least electronegative, followed by bromine, and then chlorine. What types of orbitals overlap to form for CH4? So there's my CH4. It's tetrahedral. So I need 4 equivalent orbitals. So I'm going to form 4 sigma bonds, and that's going to be each s only has, or each hydrogen, sorry, only has a 1s orbital. And then that carbon has to hybridize and give me 4 sp3 orbitals. So what I'm going to get is overlap from the 1s orbital in hydrogen to the sp3 orbital in carbon to form those sigma bonds. All right, place the following in order of increasing dipole moment. So I've got CH4, tetrahedral molecule, but all hydrogens. I've got CH3Br, and CH3F. So very little electronegativity difference between carbon and hydrogen, and all the molecules around or atoms around carbon are hydrogen. So this should have the smallest, or probably I would say no dipole moment. Now I've got a bromine, which is relatively electronegative on one end of the molecule. So I would predict that this would have a small dipole moment. And then now I've got a single atom of fluorine, which is extremely electronegative. So because there's a single one, it's really able to localize or pull all that electron density to just one side of that molecule. So this one I would predict would have a large dipole moment. So the order here should be 1, 2, 3. And again, A and B were both the same answer, but the correct answer. So if you bubbled in either A or B for 12, you got the credit for this. Which element can expend its valence shell to accommodate more than 8 electrons? I'm looking for, out of all of these, which one is in the third row or lower. Could be the fourth row, fifth row, whatever. The only one there is iodine. Nitrogen, fluorine, helium are all either in the first or second row of the periodic table, so they cannot have an expanded octet. Which element, what would you predict to be the bond order for N2? So if we look at N2, we should have sigma bonding, sigma antibonding, pi bonding, sigma p bonding, then pi p antibonding, and sigma p antibonding. So I've got sigma s antibonding, pi 2p bonding, sigma 2p bonding, pi 2p antibonding, and sigma p antibonding. With N2, I've got 10 or 5 valence electrons for each nitrogen for a total of 10. So as we start to fill this, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And I've got 8 of those electrons in bonding orbitals and 2 of them in antibonding orbitals. So my overall bond order here should be 3. And that also correlates to the triple bond that we would see in nitrogen, and that makes sense. That's what we see with N to N is a triple bond. All right, now we've got oxygen, we got O2, O2 minus, and O2, 2 minus, and we want to know which should have the strongest bond energy. So we've got sigma bonding, anti-bonding, sigma p bonding, pi 2p bonding, pi 2p antibonding, sigma 2p antibonding. So in this case, oxygen O2 should have 6 plus 6 should have 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now I have 1, 2, 3, 4, 5, 6, 7, 8 electrons in bonding orbitals and 1, 2, 3, 4 4 electrons in antibonding orbitals. So the bond order for this one should be 2. So here, we'll write this over here. O2, bond order 2. All right. O2 minus, in this case, I'm going to have 6 plus 6 or 12. The negative charge gives me 1 additional electron. The open spot is going to be right there, which is in an anti-bonding orbital. So now for O2, 2 minus, I have 8 minus 1, 2, 3, 4, 5 anti-bonding electrons. And now the bond order here should be 1.5. Oops, sorry. And then lastly, we have O2, 2 minus. So now I have, there we go. 6 plus 6 is 12, plus 2 additional electrons is 14. So we have 1 more electron. That's going to have to go there and pair up with that one in that antibonding orbital. So now for O2, 2 minus, we have 8 bonding. 1, 2, 3, 4, 5, 6 antibonding. So our bond order here should be 1. So we can see O2 has the highest bonding order, should mean it has the highest bond energy or largest, strongest bond energy there. All right, 16, use the Vesper model to predict the molecular geometry of the central atom of ICl4. So CL4. There we go. Minus. So iodine has 7 electrons. Chlorine has 7 electrons. 7 times 4 is 28. And we have a negative charge, so we should have one more on top of that. So we should have 36 valence electrons. Iodine, I only have a single iodine. So again, I'm probably going to put that as my central atom. Chlorine has that one lone pair. So I'm going to use that to form single bonds now between all the chlorines and the iodines. And then if each chlorine has 6 unpaired electrons around it, then I want to start counting electrons. 6 times 5 is 30. I have, oh, I did an extra. I'm sorry. That's what went wrong. We did an extra chlorine. Okay. Let's erase this. Okay. Sorry. So we have 4 chlorines. Each one has 4 or 6 electrons around it. 6 times 4 is 26 valence electrons. We have 4 bonds. There are 2 electrons per bond. So right now, with the lone pairs on the chlorines and all the bonds, we have 32 valence electrons, leaving me with 4. So I'm going to put a lone pair on the iodine here, and we should see the formal charge for all the chlorines is 0. The formal charge for the iodine, 1, 2, 3, 4, 8, so -1. So this would give us a molecule that overall has that -1 charge. And then if I have 2 lone pairs on the iodine, I have a total of 6 electron groups, 4 bonding, 2 non-bonding. This has an octahedral electron geometry and a square planar molecular geometry. Okay, true or false, the volume of a gas is inversely proportional to its pressure. That's true. I think it was either V1 over P1, or I might be flipping it. But you can see as pressure increases, the volume would have to decrease for them to be equivalent. Or if you think about the ideal gas equation, if N, R, and T are constant, if P goes up, V would have to go down, and vice versa. So that would be true. All right. I'm going to have to stop here because unfortunately I've got to go meet someone. I will do a second video covering the very last 4 questions on the exam.